everybody. This is Mike Urbans with It's Your Water. Today, our podcast is going to cover some pH questions. pH in water is extremely important. I don't want to call it our problem water series, but mostly what we talk about on this podcast is common water issues and how to solve them. And we interview local experts and get their input on how to solve, extreme problems. But pH is a foundation question or a foundation of almost all water treatment. And we're going to talk with our expert today is Justin Mest with Master Water Conditioning. Justin is the son of Richard Mest, who many people would know is very extremely active. So is Justin in the WQA. But Justin, tell us a tiny little bit about yourself, and thanks for doing this.
No problem. Thank you. And to answer your initial question, the company was started in 1967 by my grandparents and my uncle, actually, and changed hands, a couple decades ago. And I've been with the company for full-time about 10 years. I've been involved in water treatment my entire life, though, of course. I used to be a free family labor every Sunday, pretty much. We would make water sample bottles in our living room as a family. We'd do that, after church for an hour or two, and then we would have Sunday brunch or whatever you want to call it. And then I basically done every job at the company at this point because when I was a teenager and they needed help out in the warehouse, for people who are longtime customers, my nickname back in the day when I was 13 or 14 years old was actually Mr. MBA 30, because I used to come in 2 summers in a row, 3 days a week, and do nothing but make MBA 30T 1 cubic foot Logix-based water softeners 24 hours a week, and that was my summer job for a couple of summers. One of our employees that goes way back actually still calls me that sometimes.
That's great. I get called other things, but a lot worse than that. But
yeah, it's not the worst nickname. Then, like I said, I've been here full time for the past 10 years and started just working in the lab and sort of, people retire, people move on, taking on more responsibilities. And for the past few years, I started running what we call our science and technology department. But really, as soon as I got out of the lab, I've basically been a corporate ride X factor. I really tell people, well, my job is to do whatever the heck they need me to do on any given day of the week. Mm-hmm. So do a little bit of everything.
So one of the most tricky things that we do out there is pH correction. And this is going out to everybody who I'm assuming knows what pH is. It's the potential of hydrogen, I believe. And
that's sort of loose nomenclature. It's really pH stands for the negative logarithm of hydrogen. It's actually pH. P is a mathematical symbol. Mm-hmm. But yeah, the loose nomenclature is people like to say potential hydrogen, which in lay terms that is fairly accurate.
And one would think we always have to shoot for, we're looking for water treatment purposes in groundwater, but also where pH really played a major role in the national spotlight was Flint, Michigan. They switched a water source and the pH was lower than what would cause corrosion, saying, we can really geek out here, and I'm going to try to avoid that. But all corrosion stops at about 8.2 that we've always said. So they were down in the 6.5 or 6 range.
They were actually, pHs vary seasonally and from time to time. And that's actually, I think Flint is a perfect place to start too, because Flint was actually less of a pH issue, more of a corrosion issue, which is a really important point to make. Today we're going to focus mainly on pH, but corrosion and pH, while pH is intimately related to it, it is a sort of separate topic in upon itself. I like to tell when I do trade shows all the time, one of my favorite things to say is non-corrosive water a neutral pH does not make. I always like to throw that out there to get people to think, if you really want to look at corrosion, you need to look at a lot more than just pH. But that's we could talk about that for literal days. So yeah. I think focusing on pH is a good idea. But the average pH of the Flint River water was indeed lower than the typical pH range of the Detroit water, but the pH of the Detroit water itself would have actually caused the same issues as the Flint River water. The biggest differences were really when they switched to Flint, the pH actually started a little above 8 and then gradually made its way down over the course of, I think it was 4 or 6 months to around 7.3, or 7.3 rather. But the key was that they weren't using orthophosphate, and Detroit was. And orthophosphate was essential to helping to protect the pipe. And in super lay terms, orthophosphate functions to form a protective coating on the inside of the pipe, and therefore the water never, quote unquote, touches the lead.
Right, if it's applied correctly and blah, 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 you know. And so they just, it's just cause and effect.
The other issue in terms of the difference between the Detroit water and the Flint water, or Flint River water rather, was something called the chloride sulfate mass ratio, or the CSMR. The CSMR of the Detroit water was around 0.45, and the CSMR of the Flint River water is 2.04. And that may not sound like a big difference, but where you want the CSMR to be is ideally below 0.5. And the reason that's important is because the majority of lead corrosion comes from galvanic corrosion of lead, so something like lead tin solder. Mm-hmm. And as the CSMR increases, the degree of galvanic corrosion increases greatly. So that's one of the reasons why using the Flint River, between it was no orthophosphate and the increased CSMR, that's really what caused. And the pH was related, because if the pH was higher, the solubility of lead in the presence of that water would be lower. But really, to get good lead corrosion prevention from pH alone, you're looking at a minimum pH of 9. Yeah, really closer to 10 is good.
The bottom line is, it still blows my mind that they use lead mains. You know, it's just
there's a massive infrastructure issue that it just needs to be addressed in this country.
I think they stopped using lead pots back in the day. They probably, because it caused some mental issues, obviously, but. Yeah, that always just, I couldn't get my head around it. We had a hunting cabin, and they ran lead from a groundwater source, a lead pipe, for 600 feet. And we dug that up, and we couldn't believe it. And, of course, we put a poly pipe in, and we made lead sinkers, fishing sinkers out of all the pipe. Yeah, that indeed is an issue, and that's why they're replacing a lot of the mains. But for us and the people who really come to you and I, Justin, is the groundwater treatment people, the well drillers, the plumbers, the water treatment dealers, trying to correct groundwater that has a low pH below 7. There's several different ways that we treat pH, because you want to elevate the pH, obviously, to make certain post treatments like iron removal work better. How the pH actually keeps things in solution. We have treatments that are available to us is the calcite, which is calcium carbonate ground fine in a bed. And we have chemical feed problems not problems, but there's issues, cause and effect. It would be the soda ash, some of the polyphosphate soda ash that we would. And what chemicals to avoid, like sodium hydroxide, when we're treating well water and residential water. You don't want to fool with that.
Yeah, and I would generally agree with that. There are sodium hydroxide and orthophosphate are arguably the two best tools on an industrial scale we have, but they're also very finicky chemicals to use, especially sodium hydroxide, because it's so strong. And what that ultimately translates into is, I relate it to sort of like, calcite is like a jackhammer. Things like sodium hydroxide and orthophosphate, that's like a surgeon's scalpel in terms of to sort of try to get the concept across to people. And not to mention the fact that, with orthophosphate, we're often looking at septic systems, around the country and what have you.
Yeah.
And then we're talking about elevated phosphorus levels, just like there's a reason water treatment plants or wastewater treatment plants don't like more phosphorus. Well, the same goes for local wastewater treatment systems. And then with sodium hydroxide, it's frankly just dangerous.
Dangerous. It's downright
just,
dangerous.
That for me is sodium hydroxide is you use that in a residential application if it is your last resort.
Yeah, we know of one instance where it was a community well, but it wasn't paid community. It was a huge private complex with private homes. There was a malfunction with the chemical feed pump pacer, and they used sodium hydroxide there because it was so huge, 25,000 gallons of retention time and miles of pipe. So it was commercially applied, but the gentleman thought that he could override the pacer on the chemical feed pump and just turn the feed pump on, and he forgot about it. And it practically, just think about your skin burning, like dissolving, and you have no place to wash your skin off because you have no other water source. So it could have been a complete disaster. Fortunately, he had 25,000 gallons of cushion. But if this happened in a home, you would have pure sodium hydroxide, which basically dissolves flesh and bone and organic matter due to its caustic. It's better known as caustic lye, for layman's terms. But it makes me cringe when I hear it's a scalpel. It's very well said, Justin, that if you want to surgically raise your pH, but the problem is there's no room, no margin for error. So
we're not dealing with surgeons.
We're not dealing with surgeons.
We're not dealing with surgeons here. We're not dealing with people that
plumbers
are used to life and death situations. We're dealing with, a little less...
exactly. They may think they're surgeons, but, hey, water treatment guys and plumbers and well drillers, it's, you're going to get mad at us, but don't fool with it. That's what Justin and I are trying to tell you. So, and what we're going to talk about is basics on the application of calcite, the pitfalls and the pluses and minuses of that, and then sodium, not bicarbonate. I had person put that in.
Yeah, it's sodium carbonate. You got it right.
Sodium carbonate, soda ash, as we know it, or there's a couple brands out there that have a polyphosphate built in to keep the injection site clean, but with a little bit of poly in there. But most of the time, we're just talking about soda ash and a calcite. So for the time purposes here, I know it's a huge subject and we'll probably come back, but your do's and don'ts of the calcite, where we see the major problems with applying calcite, which is a granular product that's applied through contact of water. So the water flows through a tank, usually with 150 to 250 pounds of a specific calcite, a graded NSF approved drinking water natural product. And you're simulating Mother Nature, and you're basically flowing the water through the calcite bed and out to your house, buffering the pH, correcting the pH. But what do's and don'ts? We're just giving people just little tools here, and they can contact us after the podcast. But we're just trying to give you hard and fast do's and don'ts here.
Yeah, and I think the most important one is properly test your water. That should be a given. Sometimes it's not, but that really should be a given. And I know most people out in the field are testing pH, hardness, and iron. Maybe they have a TDS meter. For me, the bare minimum, the absolute bare minimum analysis, if you want to properly apply any pH correction, even something as simple as calcite, you want to be testing the total hardness, the iron, the pH, the total dissolved solids, aka TDS, and also either the total alkalinity or the free carbon dioxide. That fourth or fifth option, that is the most important one, in my opinion. And it's something that most people, when I do classes and I talk about free CO2 and total alkalinity, most people,
They don't
they glaze over and they have no idea what I'm even talking about. And that pH is all about a ratio of total alkalinity and free CO2. And free CO2 and total alkalinity have the largest impact of anything else in terms of what happens when we flow water through calcite. So that's something you should most assuredly be testing for as far as I'm concerned. So that's the first big do.
Very important for us.
Test your water properly. And I also strongly encourage people to invest in a pH meter, not a color indicator. Color indicators are, in my opinion, perfectly fine for spot checking performance. I personally myself get very nervous trying to apply pH correction using a color indicator. If you're applying something, my advice is test it with a properly calibrated meter. If you then want to use a color indicator to check your treated pH just to make sure it's like 7.75 or 7.578, that I have no problem with. But another note about color indicators, they are not very accurate at very high pHs and very low pHs, and at very high total alkalinities and very low total alkalinities.
It's interesting.
So if you're usually like 6 to 7.5 or 6 to 8, and your total alkalinity levels are relatively moderate, yeah, it's going to be pretty accurate. But when you start getting outside that range, and if you run to the extremes of total alkalinity, you're probably going to find yourself in trouble. So that's another big do for me. Do invest in a pH meter. And pretty much all pH meters now have automatic calibration, and any pH meter, even a pocket tester worth its salt, is going to have incorporated automatic temperature compensation. Mm-hmm. So, the pricing has come way down. And please calibrate your meter.
Well, yeah, they're fussy. I know they are fussy, and you have to calibrate.
You should calibrate them at least once a day.
The same with your TDS meter. Buy a good one, and you get what you pay for. Myronell has a good couple new ones out there in the $200 range, but that's where you're going to be. I think a pH meter is probably a little bit more.
You can honestly get a decent pH pocket tester, which I would trust any day over a color indicator for like $80.
$80.
Yeah, they've come way down in price. A good one, the pH meter I use in my test kit costs $600.
Right. Yeah, you're professional. You're making sure we're giving out advice, but
I understand that most people aren't going to want to spend that kind of money.
Yeah. The part of this podcast, what I'm basically want is to imply that and I'm so happy that's what Justin does, is that he just told you that the testing and the tools are so important to get to us, and the size of the home, the flow rate, the pump flow rate, the drawdown, the size of the pressure tanks, because we're talking well water mostly. For our purposes here, it's groundwater with a low pH, which we find mostly East Coast. So.
And you brought up a good point in terms of the number of bathrooms and the well pump flow rate, because, you have to strike a good balance of, you need to meet a certain service flow rate, but you also got to make sure that you can properly lift your bed and rinse your bed out. And if you're, sometimes we have a situation where you may have a fixture demand that indicates, or in other words, you may have enough water using fixtures in a home to indicate that you may need a peak flow rate of 10 GPM, but your well pump's only giving you 5. Well, how do you handle that situation? Because obviously, if your well pump's only reliably producing 5, but then you probably have a bladder tank where you're temporarily getting higher flow rates because you're boosting the pressure and what have you, well, then you find yourself in a situation where, okay, rather than I can't use one big tank to treat 10 GPM, I need to use 2 small tanks to be able to treat 10 GPM, but also be able to properly backwash and rinse my calcite. And that obviously leads us into flow rate design. And another really common mistake that people make is, not properly sizing neutralizers. And I'm sure several listeners have probably seen where if they really pay attention to their pH, if you've got, if you test your pH through a calcite filter when you're just running a kitchen sink and it comes out like right at 7.2 where it should be with calcite, but then someone's doing laundry and two people are taking a shower, and then you take a sample in that scenario and all of a sudden your pH is 6.5. Well, it's all about contact time, right? And in neutralizers, we like to, in the residential arena on a manufacturer level, when you see flow rates on specification sheets, my advice is always think of that as a peak flow rate. That's not a sustained flow rate. We're guilty of that too.
Yeah.
We talk about a 13 by 54 neutralizer like it'll treat 6 to 7 GPM. And for me, that's a peak flow rate. And frankly, a lot of my competition will tell you that I'm crazy and that no, a 13 by 54, you can get 10, 11 GPMs out of that. Yeah. And I call total BS on that, frankly, because really that 13 by 54 neutralizer, if you were talking to someone like an engineer or someone who, like certified systems operator,
right,
they're going to tell you I'm crazy for the opposite reason. And I would factually agree with them because, a 13 by 54 neutralizer in terms of a more continuous flow, it's probably more like 3.5 gallons a minute, not 7.
Right.
So
peak is not, and for the uninitiated out there, just you can close your eyes and picture a tank that's 13 inches round and 54 inches high with 250 pounds of calcite, not buffered, not with, we can add a buffering agent, which would be magnesium oxide. There's with pH, if you can hear, the underlying thing is, it's not an exact science, and almost every home is different. Every application is different in that some flow more, some flow less, and we're using calcite, which is very convenient. It's very nice. It's just a tank full of carbon. I've been talking carbon.
Yeah,
a tank full
of
carbon
your whole life.
My whole life. A tank full of calcite, and you have, the bigger the tank, the better. But if you don't have enough well pump to backwash that tank, you say, well, why don't we put a huge tank of calcite in there?
Because then your media is literally going to turn the concrete
turn to concrete, right? So it's a crazy thing, but I would say, how many calcite systems do we sell versus chemical feed?
For
a lot more.
For me, and this is another thing I really preach a lot when I'm teaching classes at on an industry level, is the notion of, when we look at residential water treatment across the board, I don't care what technology we were talking about, when we look at residential water treatment, our world is all about compromise, right? There's a way we should do things, and then there's a way we can do things. And calcite, for me, is the perfect example of that, because is calcite easy? Yes. But like you said, there's always a give and take. With the easiness comes in some people's mind, lackluster performance. But at the same time, those same people are the kind of people like the EPA. As far as the EPA is concerned, at this point, basically, in their opinion, you bring your pH to 7.2 to 7.8 and you use orthophosphate. Everything else probably isn't going to work. Imagine if every single water treatment dealer had to do that. Every single surface water body on the face of in the country would be having algal bloom issues left and right. Like, I don't know if you're familiar with Westtown Lake, but Westtown Lake is one giant ball of algae. Basically every surface water body would look like that if we used orthophosphate on every job.
It's food.
Plus the maintenance nightmares. So instead, we use things like calcite or calcite and magnesium oxide blends. And the benefit of them is just like you said, it's the ease. And are they perfect performing? No. But when you look at the trade-offs of because another thing we have to consider here is what is practical to expect of your typical homeowner. Mm-hmm. The typical homeowner probably isn't going to be willing to and may not even be able to properly maintain even something like a soda ash injection system.
Soda ash injection, which is which is a little segue here. And here's the convenience factor plays in. A soda ash is a solution that the homeowner must make. An ingredient he puts in his powdered sodium carbonate, which is soda ash, and you have to mix it with, warm water, which would be nice.
Probably softened water.
Softened warm water, so it dissolves. So you're dissolving You're making a batch. So you're making a batch of soda ash water that will be able to be in usually a 30-gallon storage tank, and then you have a chemical feed pump, which is an injection pump that injects the soda ash liquid into your water pipe via a check valve, and the feed pump pumps at a higher psi than your house water. So then it just inject every time your well pump comes on or a water meter initiates flow. It initiates the operation of the chemical feed injection pump. They're more efficient because now you can calibrate the injection pump to the flow of the water of your house. So here we get a little more surgical with a chemical feed pump.
Yeah, and it allows
accurate.
you to and accuracy. Yeah, accuracy is key, and it allows you to go back to calcite real briefly. One of the pros and cons of calcite is that it has self-limiting properties in the sense of once you get all of those fines rinsed out, unless you have some mineral acids present in your water, that pH at properly sized and properly designed, in other words, assuming you don't have too much free CO2 or total alkalinity or too much total hardness in the water, your pH is probably going to come out of right around 7.2. That's nice because you don't really run into overcorrection issues with calcite. The downside is, we mentioned earlier about lead. For lead reduction via pH alone, you really need your pH to be around 9. Well, at least on a theoretical level when it comes to corrosion, even for copper pipe, we want our pH really ideally to be at least 7.8. You're never going to get there with just calcite, which is why we often throw in a little bit of magnesium oxide to get that pH up a little bit higher. That's an important thing to note about calcite. And to go back to soda ash allows us to really dial in that pH. And if you really want to get into it, you can say, okay, you can look at a bunch of different water quality parameters and say, okay, my pH, I want it to be here for this specific application. And a feed pump allows you to say, if you want to be 8.3, you can come pretty darn close to consistently maintaining an 8.3 pH. So, that there are benefits to something like a soda ash injection system, but the con is
you got to go down the basement.
You got to go down there. You got to
wear
mix
a mask because soda ash is a powder. It's it'll irritate mucous membranes, and it's not dangerous like the caustic.
You ain't gonna melt your skin, but
you're not gonna melt your skin.
Can irritate your lungs.
It'll irritate your lungs. Plus, and it has a tendency to cake for the lazy batch maker. If you just pour it in and do a whirlpool of water in there and you say, oh, we're fine, it precipitates out into chunks, and in the bottom of your batch tank can then become sludge. And but if you're willing, or you, in most cases, you don't have a choice, you have to go to soda ash. You can opt for a maintenance contract with the installer, or you do it yourself. But
I mean, that does bring up another good point that I like to mention to people too. When it comes, because some people are really afraid of soda ash injection systems because they don't want homeowners maintaining things. Well, if you need it, you need it. So, potentially, I'm not really a business type kind of person, but even I can see, well, maybe we try to spin that into service contract.
Yes, definitely.
That is one way to think about soda ash in terms of a pro of the process. Yeah, it's all about, for me, the two key comparisons are sometimes you just can't use a neutralizer for any number of reasons, and sometimes you just have to use soda ash. But outside of that, soda ash gives you control.
So, yeah. And again, the bottom line here, just because we would want to lose you and everybody's starting to fall asleep, I can hear you out there, because I want to conclude with a really not controversial subject, but something that's taken the water treatment, the wild, wild west of the internet. But we're going to conclude with that. So stick around. But what you could take away is it's incredibly important to get testing equipment, quality testing equipment, or quality test results. Do your forensics with your house, the size of the home, the flow rate of the house pump, and let the experts take it from there. And then slowly but surely, you will become an expert from osmosis, from us telling you. I mean, we could, again, talk, pH is a big, big issue, but hopefully everybody here understands the takeaways, and that's why we have this podcast. But the last thing here, and what has taken, speaking of pH, Justin, which has taken the internet, I'm trying to bite my tongue.
I know exactly where you're going.
is this idea of high pH alkaline water being a new homeopathic, healthy something or other. And I can't get my head around it because your pH of your stomach is what? 2? So you're dumping alkaline water, which is high pH. So there are gurus out there saying, if you drink alkaline water.
Gurus, quote unquote.
Yeah, quote unquote. Internet gurus saying alkaline water is healthy. I have yet to see, and it's usually just like anything else. It's testimonials. There's no valid science or validation through the American Medical Association or anybody. It's usually hearsay and people's testimonials. Since I've been drinking it, my hair stopped falling out.
One of my least favorite terms on the face of the planet, anecdotal evidence.
There you go.
I hate anecdotal evidence. So I actually, a few months back, I finished serving on a WQA task force where we were actually tasked with investigating whether or not we wanted to take an industry position. Well, we weren't making that decision. We were tasked with doing the research to report to the people to make the decisions about whether or not, we even wanted to take a position on it. And my opinion on the matter is that there is some sloppy science, I'll say, that does have enough data suggesting that there may, very heavy emphasis on the word may, be some benefits within certain categories. But it's important to lead with, we need to understand how the scientific process works. Science is all about repeatability. If you can't repeat a result, then your result is functionally worthless in the eyes of the scientific community, and rightfully so, because sometimes there's a goof and something just happens, and the people who reach that conclusion don't realize the goof, and then someone else tries to replicate it, and maybe someone else. It's just like sometimes you need a third set of eyes, right? The same thing happens in the scientific process. That's why you have peer reviews, and that's why you need repeatability in studies. And there's one of the biggest issues with alkaline water is the limitation in studies. And most of them tend to be very focused, and then no one ever really does a follow-up study. It's just sort of, okay, this is one study's results, and it indicates these things, and sometimes their mindsets are flawed to begin with, but then if you don't try to repeat the results, then once again, they're functionally meaningless. So that's one big part of the issue, is just weakness of study design. In terms of one of the most common issues is not properly accounting for confounding variables. Also, very small sample sizes. It's hard to do proper human trials for pretty obvious reasons, but in order to really draw truly causal relationships, something like epidemiological population study doesn't really get the job done, because there are too many confounding factors to even try to account for all of them. So those are some of the main issues with the studies. But my advice to people when it comes to drinking alkaline water is, first of all, whenever you're trying to make any sort of dietary decision, and your drinking water is a dietary decision,
huge,
you should always consult with an appropriate physician. Because, I'm not a physician. Mike's not a physician. I can tell you what I've learned from my experience researching the subject, but humans are finicky, inconsistent organisms. So something that might not hurt me might hurt Mike, and vice versa. So please don't just if someone asks you about alkaline drinking water, don't just willy-nilly completely disown it or completely embrace it the best thing you can tell your customers is, well, first of all, you should be having this conversation with your, GP.
Yeah. That's what people say. My skin, will soft water help my skin? I said, I'm not a dermatologist.
Yeah.
I'm maybe, but yeah, talk to your dermatologist, talk to your doctor. Well put. And I think
so that's the most important thing. But when it comes to the potential benefits, I think, first of all, most of the grandiose claims you read on the internet about it cures cancer, it prevents cancer, it increases your systemic pH, all of those, there is no legitimate evidence to promote any of that. That, and in my opinion, that's irresponsible marketing, because if you're going to try to tell someone who has cancer that drinking alkaline water may help them, you're giving that person that's in a very unfortunate situation false hope. You're essentially preying on a wounded animal.
Mm-hmm.
In my opinion, on a personal level, that's just not good.
Yeah.
Don't do something like that. As far as potential benefits that have been at least loosely demonstrated, the evidence suggests that there may be improved hydration after strenuous exercise specifically. And it's worth noting that all of these studies are done on athletes, practicing athletes. And obviously how a practicing athlete's body recuperates is not the same as someone like me who, works all day and then goes home and plays video games and passes out. That's like the cycle of my life.
That's right.
I'm going to recuperate after strenuous exercise different than a professional basketball player.
Me, it's Jack Daniels and cigarettes. I just, right, with a remote in my hand, they find me and I come back. No, just kidding, folks. But with that, this is a big subject. We went past our normal time, but hopefully everybody stuck with us here. So thanks, everybody. It's your water. And thanks, Justin.